Today what we are going to learn is the membranes, modules, and cassettes for the MBR process. Last time we studied some of the important models and equations, and we'll continue to talk about that. And one of the most important equations that you have to remember is this one. So the relationship between the cake resistance and specific cake resistance and the cake mass, which is shown in this equation 4.2. So the RC is proportional to the cake mass per membrane area, and this correlation coefficient is the specific cake resistance, which is shown as alpha. The unit for alpha is meter per kilogram, so this is another thing that you have to know. And this equation can be extended using Karman-Kazan equation, so that leads to the other equation on this page. So the alpha is shown as a function of this particle diameter, porosity, and particle density. So that equation it can be obtained by using this Karman-Kazan equation. So if you wanted to calculate cake mass using the information of particle size and porosity, this equation is very useful. Although this equation uses a lot of assumptions, so the theoretical calculation and experimental data may not match very well, but at least it can actually have some initial projections, and sometimes for the interpretation of the experimental data, this equation can be used. So that's why you have to remember that. To use the equation in the previous slide, you have to know the information on particle size and porosity. Particle size can be measured using laser scattering techniques. However, the porosity of the cake cannot be directly measured using conventional techniques. Fortunately, recently, people have invented the technique so-called confocal laser scanning microscopy. This technique is useful especially when you deal with the cake formed by microorganisms, because it uses fluorescence dye which is specific to some microorganisms, and this technique allows to have some three-dimensional image, and by doing some image analysis we can actually calculate the porosity of the cake. So so this technique is especially useful for getting information on this biocake, and the bacteria in the cake layer is stained first, and by having some special techniques we can actually have these images using CRSM. So this is actually the examples of the images from CRSM techniques, and CRSM is actually what we can get from this CRSM is a series of images at different positions, different Z positions. Z positions. So we can have series of images, and we can interpolate between images so that we can actually have a continuous three-dimensional the object in the computational space, and by having some mathematical calculation we can actually find out how much cells are encoded in this space and how much void space exists inside this. So that's the basic idea of CRSM. In fact, by using different dyes, we can actually have the porosity for the microorganisms, and we can also have some information on these extracellular polymeric substances during this biocake. So this is CNSM technique is an essential one for the MBL techniques, MBL process. Using CNSM, we can actually have the information at different space, different positions, and we can also have information at different time spans, at different times. So, for instance, if you monitor the biocake on the membranes in MBL during some period of time, we can actually see how the biocake are evolving and developing during the MBL operation. So this picture shows how this biocake forms with these MBL operation times. So initially we can have a lot of space, a lot of void space inside this cake layer, but as this time goes by, we can actually see very dense cake layer formed on the membranes. We can actually see that from the top or from the bottom, and that is actually a very, very comprehensible information on the characteristics of this biocake. Here we'll see another classification of fouling by location of fouling. So the fouling may happen on top of the membranes inside the pore and something like that. So depending on that kind of the positions for the fouling, we can actually classify different fouling phenomena. So first one is internal fouling, and in this case the foulant, which are smaller than the pore size, can penetrate inside these pore structures, and it can actually narrow down the pores of the membranes, and so that's actually the problem of this internal fouling. So from the early stage of filtration, adhesion occurs when dissolved materials and colloidal particles in the feed solution for the MBL to attach to the pore entrance and pore walls of the membranes. So it leads to the narrowing of pore diameter, and then we can see a decreased permeability of the membranes. And this fouling resistance is actually happens in the early stage, because once the cake layer formed, this internal fouling may be retarded. So generally speaking, the predominant fouling resistance is the cake layer resistance rather than this internal fouling, especially in MBR process. If you compare the solid deposit patterns, there are actually three typical types that we can generally observe in the membrane process. The first one is the cake layer formation. Second one is for narrowing, and the third one is for plugging. Cake layer formation occurs when the particles are much bigger than the spore size, so they cannot get into the membrane pores. So it will form a layer of particles which can actually reduce the hydraulic permeability of the membranes. So, and for plugging happens when particle becomes stuck in the pores of the membranes. So we even call that this is for blocking. And so for narrowing happens, as I mentioned, that when solid and particles smaller than the 4 diameter exist in the feed solution, they deposit onto the membrane surface as well as the interior 4 walls, so that we can actually have the reduction in effective 4 diameter. These individual fouling patterns never occurs separately or independently, which means it happens all the time together. So they can see everywhere, every situation, but sometimes one of these mechanisms is more dominant than the other ones. So that's we can that's why we sometimes analyze the dominant fouling mechanisms. When we consider the MBL, the individual fouling patterns cannot be observed, separately. These are the schematics of different fouling patterns that I already explained. So if we have very small foulant, solute adsorption to forward can be observed, as you can see just here. On the other hand, if the particle can block the for entrance, we can see this kind of phenomena. So particles having the size with the diameter will result in for plugging. Cake layer formations, when we have particles much larger than this 4 size, sometimes if the particles can aggregate, even smaller particles can form this cake layer. But normally when particles are bigger, we can see this cake layer formation. And in ambient systems, we have 3-phase flows: air, mixed liquor, and microbial flux, and their distribution is determined by these hydrodynamic conditions given by these membrane modules, aeration, and feed water supply. When we look at this solid fouling, there are a couple of things that we have to consider. The first one is concentration polarization. Concentration polarization due to concentration gradient formed near the membrane surface, and it also happens in MBL as like all the other membrane filtration process. However, in MBL systems, concentration polarization exists in a very, very small range of distance. So this is very close to the membrane surface. So if you consider the membrane, the MBL process where this cake formation normally happens, concentration polarization happens actually inside the cake layer, so that we can simply it is not simple to distinguish the effect of concentration polarization from the data of this cake formation. So that's why people don't normally mention about this concentration polarization. Gel layer formation happens in ambient systems, and it looks similar to the cake layer formation. Strictly speaking, gel layer consists of highly concentrated solid and macromolecules rather than particles. So although it looks just like cake layer, the composing material is a solid or small colloidal materials. And the main driving force for the gel layer formation is the concentration polarization. However, gel layers are easily incorporated into cake layers, so again, it's not really difficult to distinguish this gel layer formation from cake layer formation. So we can just treat this gel layer formation as a part of this cake layer formation. This picture shows the types of foulant in ambient systems. In ambient systems, we have this mixed liquor, which is feed water to this membrane, and we can distinguish these the foulants into this mixed liquor into two groups. The first one is the particle, and the second one is soluble matter. And particles include the microbial cells, cell debris, and sometimes we can have like other debris like grit, hairs, and silt in the ambient system. And microbial flux are main components in the particles in the mixed liquor, and it includes these microbial cells as well as bound EPS. On the other hand, the solid matters include the free EPS or SMP, and inorganics such as calcium, sodium, magnesium, something like that, and unmetabolized feed components like organic matters. Let's look at one by one. The particles. Since the membrane filtration is basically a sort of solid liquid separation, the particles should be primarily considered as important foulant in ambient system. So that's why we normally see the cake layer formation as a major fouling mechanism. And flux are the main components, as I mentioned that. And individual microbial cells are interconnected by EPS and cations such as calcium ions, and this leads to a formation of 3D structural matrix or flux, and the constituents of the flux are embedded into a polymeric network of EPS. The MLSS is a basic component comprising bulk solution in the activated sludge. Therefore, the effect of MLSS concentration on membrane fouling is a very interesting topic. Sometimes we see that as we increase MLSS, the fouling is accelerated, but sometimes we see that there's a very weak relationship between the MLSS and this fouling propensity. So the fouling tendencies associated with MLSS concentration are inconsistent and contradictory sometimes in some cases. So that means there are other factors affecting the membrane fouling in ambient system. Flux size is another very important parameter affecting the ambient membrane fouling. And sometimes we have these different sizes of the flux in this mixed liquor, and even the flux size distribution of the X-phase large suspensions with different MLSS concentration, which you can see from this picture. So when we have this MLSS of 100 milligram per liter and 4,000 milligram per liter, actually the particle size distributions are different. So that we can see that the particle size is shifted to the right side, which means as the MLSS increase, in this case, the particle size, average particle size also increase. If you look at the particle size, most of the particles in the mixed liquor of the MBL feed solution, MBL in the MBL reactor, are actually the set level solid particles, which means the particle size is bigger than 50 micrometer or 100 micrometer. However, if you just look at the impact of the particles on the membrane performance, small particles are more important, and that you can just imagine from the Kalman-Kozeny equation, which shows that if the particle size is smaller, the cake layer has lower permeability, which means same amount of the particles can form more impermeable cake layer. So the number of particles, small particles, are more important. And if you just look at the volume particle size distribution, the larger particles exist most in the mixed liquor. However, the number of small particles is greater than the set level particles if you just look at the number. So that's why we have to look at the existence, the relative importance of the small particles. Most membranes used in MBL plants belong to either microfiltration or ultrafiltration. And in this case, a submicron pore size, they have a submicron pore size, and their particle size, the pore size is similar to the small size of the small particles in the mixed liquor. So pore blocking may happen, which has more severe impact on the membrane performance, and this will cause a more severe membrane fouling. There is another reason why fine particles are important in fouling process. And so the particles in the cake layer are compressed by this convective flow, and these particles cannot be easily removed by this back transport. If the particle size is smaller, the back transport velocity is smaller, which means they cannot be easily removed by flow motion near the membrane surface. So we normally do aeration or other flows to scar these fouling layers from the membrane, but if the particles are smaller, this kind of scoring effect will be less significant. This results in a diminished effect of cake removal, so this will eventually lead to insufficient cleaning. Therefore, particle size is one of the most important parameters affecting the membrane fouling. The average block size in conventional MBL ranges from 80 to 160 micrometer. Of course, it depends on the microbial physiology and influent characteristics and the site of the treatment plant. And but the average particle block size in the side stream MBL, which is not conventional. Conventional MBL is submerged MBL, but side stream MBL has smaller size, smaller particles because of the recirculation of mixed liquor. So that's why side stream MBL may have more severe membrane fouling compared with the submerged MBL. And that's another. This is another reason why submerged MBL is more practical compared with this side stream MBL. Evaluating the fouling propensity by the mean particle size based on the volume frequency might not always be adequate, because this volume average cannot properly reflect the importance of the small particles. Even though the overall volume occupied by fine particles is much smaller than that of the big particles, the number of fine particles is obviously greater than that of the bigger particles. So that's why we cannot just rely on the volume average particle size. So this is a typical situation that although we have very small number of small particles, if you look at the volume particle size distribution, and if you convert that to the number particle size distribution, the solid line is converted to this solid line, which means actually if you just look at the numbers, the particles smaller than 1 micrometer are actually the majority of these particles. So the number of particles which has the size less than 1 micrometer is the largest in this situation. So if you look at this solid line and broken line, their difference may not be significant if you look at the volume distribution. However, if you look at this number distribution, you see that these two distributions are quite different. So that's why we always have to analyze not only the volume frequency but also the number of frequency. If you talk about this fouling in ambient system, one of the key factors is extracellular polymeric substances. So without understanding this one, you cannot properly understand this fouling in ambient system. Microbial EPS are high molecular weight mucus organics from microbial cells. EPS play an important role in plaque formation and include the heterogeneous polymeric materials, including polysaccharide, protein, lipid, and human-like substances. And of course, it also contains small concentration, small portion of this DNA and RNA and nucleic acid. But if we talk about EPS, the majority of EPS consists of this polysaccharide and protein, especially polysaccharide. Yeah, that's what I'm talking about here. Since EPS provide a highly hydrolylated Gale matrix in which microorganisms are embedded, they provide a significant barrier to permeate flow in MBL. So EPS is very good if you talk about these microbial cells, but if this EPS exists on the membrane surface, it will cause severe membrane fouling. So that's why we call EPS as one of the most important foulant in MBL process. High concentration of EPS inside the flux as well as in bulk solutions are responsible for rapid fouling buildup. So if you look at the EPS, you will see the status of the MBL process, and you can also predict the fouling propensity in such MER system. So we have to analyze the EPS concentration from the fouling from the fouled membranes. So this is actually the procedure. Starting from this fouled membrane, we first have to detach the cake layer from the membrane, and then this cake layer is just a solid material, so we have to resuspend this cake layer. Then by doing centrifugation and or the microfiltration, we can have this soluble part, and we have this pellet including flux and resuspension. We do this resuspension with the saline buffer, and then we can prepare sample for EPS extraction. There are actually two methods for EPS extraction. One of them is the physical method. The other one is the chemical method. And physical method include heat treatment, ultrasonification, and high-speed centrifugation. On the other hand, chemical method include the sodium hydroxide treatment, EDTA treatment, and cation exchange resin or aldehyde treatment. And that's the extraction step. And then after doing that, we will get this extracted bound EPS solution. Then we can determine the organic content using VS or TOC. The origin of soluble matter is divided into two categories: unmetabolized feed components, which actually originate from the influent wastewater, and SMP produced by microorganisms. Both these SMP and soluble EPS are used to express the soluble organic solute in bulk solution originating from microbial excretion. They are sometimes interchangeable terms because EPS is a more comprehensive term than soluble EPS, because soluble EPS indicates only the macromolecules. However, SMP include not only the macromolecules but also these small molecular organics. However, it is difficult to distinguish both of them by chemical analysis because their basic chemical composition is very similar, because they also consist of protein and polysaccharide. So as I mentioned, that this term SMP and soluble EPS are just interchangeable, and especially when we talk about membrane fouling. SMP represent all kinds of soluble organics from microbial metabolism. EPS obviously have a polymeric nature, and in addition, unmetabolized feed components are not related to microbial excretion products, but they are categorized into SMPs or soluble EPS when they are chemically analyzed. Practically, it is difficult to analyze or differentiate SMP and EPS, no matter where they originate. Therefore, some research groups categorize all EPS and SMPs into a single group called this biopolymeric cluster, or BPC. So this picture shows how we can analyze EPS from the MRSS sample. First of all, you have to understand the difference between EPS and SMP, because EPS it exists near the membrane cells near the microbial cells, and it also exists in the form of the soluble organics. And in fact, some of these EPS and other microbial products are hydrolyzed, and it is converted to SMP. And some of them are diffused to form SMP. And SMP sometimes also include this substrate from the feed solution. So you can understand that this SMP is very, very complicated material. Anyway, if you wanted to analyze EPS, you can start from this MLSS sample, centrifuge, and the supernatant are used for the analysis of SMP, and these deposit are used first. It is resuspended, and then it is treated by heat, and again we do some centrifugation, filtration using 1.2 micrometer filter. Then we can have this EPS, the samples for further analysis of EPS. For the analysis of organics, recently FEEM spectroscopy is used because it allows the mapping of this chemical structure of these organic matters. So it can provide the information on the chemical and physical characteristics of the dissolved organic matter. And so it has been used to compare the chemical structure of influent SMP and membrane foulant in MBL. And it has some reasons that we have to look at. For instance, if you perform this FEEM analysis, you will get some positions, and each spot or each region represent some specific organics. For instance, the 390 and 472 nanometer means that terrestrial human-like fluorescence, and 301 and 392 nanometer means the microbially derived human-like fluorescence. So we all have this kind of organics assigned for each region in this FEEM map. So FEEM is actually the fluorescence spectroscopy, which means we have the excitation wavelengths, and so we actually provide the wavelengths here, and if it has the emission at a certain wavelength, it will be shown here. So if you have this 260 nanometer of this light, and if you get this emission at 325, we'll see this kind of the peak in this spectroscopy. So this is how we can determine that this organic matter in the feed solution, because as I pointed out in the previous slide, depending on these excitation wavelengths and emission wavelengths, we can actually identify the structure of these organic matters. So each region is assigned to a specific chemical structure of the organics. So by having this kind of result, you can see how much organic, how much protein exists, how much polysaccharide exists, how much humic-like organic matter exists. That kind of information can be obtained by doing this analysis. So this is why this FEEM spectroscopy is powerful, and especially when you wanted to analyze the organic fouling in the membrane system. Okay, now we'll take a look at the factors affecting membrane fouling. In fact, there are three major factors that we have to consider when we have the fouling problem. The first one is the membrane. Second one is the microorganism, and the third one is the operating condition. As you know that the membrane is the place where the pollutants are deposited, so the membrane property is very important. So if we have these materials that can attract the foulant, we'll see very serious membrane foulings. Membrane pore size, membrane porosity, and roughness, and tortuosity, and hydrophilicity, hydrophobicity, all these kind of properties are influencing the fouling propensity. In addition to membrane properties, the properties of the microorganisms are also important. As I mentioned, that the EPS, MRSS, flock size distribution, flock structure, they are all very important. Especially in ambient system, the flock structure, such as the forming and bulking pinpoint, they are like very important factors affecting the membrane performance. Operating conditions are another kind of factors that we have to consider. The cross flow velocity, TMP, critical flux, aeration intensity, they are like very hydrodynamic conditions that we have to look at. SLT, HLT, FM ratio, they are the biological factors, biological operating conditions, which are also very important. Hydrodynamics configuration, we also have to consider this. So when you have the problem of membrane fouling, you needed to have this kind of systematical approach to understand the fouling mechanisms, and based on this knowledge, you can actually have the solutions for these fouling problems. Okay, let's look at one by one. When we consider membrane and module, the pore size is first kind of factors that we have to consider. The effect of pore size on fouling intercorrelates with the feed solution properties, particularly the particle size distribution of the activate slurry suspension. We already mentioned about these fouling mechanisms such as pore blocking or pore narrowing and cake formation, and we know that pore blocking is one of the most serious fouling phenomena because it can readily cause irreversible membrane fouling. So if we have this foulant in the feed solution, which has the size similar to the pore size, will experience that for plugging problems. And so that the particle size and pore size, their relationship, it's very important. So the pore plugging is kind of this phenomena when the average pore size is similar to the size of the particles. And when we consider the typical conditions for the activated large suspension particles, we normally have these particles which has the size less than 1 micrometer, which is nearly close to the pore size of the conventional microfiltration membranes. So ultrafiltration, which has a smaller pore size, is sometimes better than microfiltration because it can actually prevent for plugging by these submicron particles. When you consider membrane fouling, um, you first have to consider this concept, hydrophilicity and hydrophobicity. Hydrophilicity means this material like water. Hydrophobicity means this material repels water. And foulants are normally hydrophobic. So, and if the membrane is hydrophobic, this can attract this hydrophobic foulant so that membrane fouling can readily occur. On the other hand, if the membrane is hydrophilic, in this case, this can repel this hydrophobic foulant, so this membrane is actually uh, more resistant to these fouling problems. So the hydrophobic interaction, which happens between hydrophobic membrane and hydrophobic foulant, is a key factor affecting the fouling problem. Commercially available membranes are in most cases polymeric membranes, and they are more like hydrophobic. So the most frequently used membrane material in MBL is polyethylene, polypropylene, and PVDF, and they are all hydrophobic. So we can imagine that this hydrophobic interaction lead to membrane fouling. So we need to make this membrane surface as hydrophilic as possible, but we cannot change the polymeric material. So the way that we can apply here is to make the surface hydrophilic while the bulk material of the membrane is unchanged, which means we can actually modify the surface of the membranes so that we can introduce some hydrophilic functional groups on top of this membrane surface so that we can actually minimize these hydrophobic interactions. The membranes used in MBL are mostly polymeric materials, and this has limited capability of handling chemicals. So pH and chemical cleaning, they can also make this membrane less efficient. So sometimes we wanted to use more stronger membranes, and one of the examples is the ceramic membrane or inorganic membrane. So ceramic materials such as alumina, zirconia, silicon carbide, and titanium oxide, they are very strong and have very high mechanical strength and chemical resistance. So they are like ideal materials for the MBL application. And only the problem is this has lower packing densities than these hollow fiber membranes, because inorganic membranes should be used in tubular monoliths, so we cannot reduce this, we cannot increase the packing density. So anyway, when we can have the problem of severe membrane fouling, instead of using polymeric membranes, we can consider applying ceramic membranes. Membrane charge is another important parameter in determining the permeability of charged ions in nanofiltration or ultrafiltration process, and this can also play an important role in preventing membrane fouling by this um, um, the charged particles. The charge interaction happens between membranes and the flux, and if the membrane is negatively charged, it can efficiently repel this negatively charged microbial flux. Um, Module design is also important. Of course, in MBL systems, we mostly use hollow fiber membrane modules, which has very high packing density, and this high packing density can reduce the number of membrane modules, and it can also reduce the footprint of the module in this aeration tank. However, overpacked modules can badly influence this mass transfer efficiency within the fiber bundles, resulting in a decreased design flux. So this slide shows the relationship between the packing density and flux, and if we have moderate packing density, flux is almost constant. But if you increase the packing density more than zero point 0.5, we can see that this packing density, the flux decrease with the packing density, which means there's some kind of mass transfer limitation, which can actually reduce the water flux through the membranes. So at some point, even if we increase the packing density, we cannot increase the water production by a module. And that's why we needed to have appropriate packing density per module. So compared with this case, of course, this packing density should be maintained at um, um, at at a proper value. So the CFD, computational fluid dynamics, this can provide more insight into the packing density optimization. So using CFD simulation and comparing this with real experimental data, we can actually optimize the module design. So there are a lot of study on this case, and one of the, according to one example, a packing density between 0.5 to 0.6 can provide a very good promise. In addition to the membrane property, microbial characteristics are also very important. In fact, mixed liquor is a very complex, heterogeneous particles containing a lot of different materials. So the fouling occurred by these microorganisms and particles and organics. Um, this fouling problem may be very, very complicated. So, and we also have to look at the dissolved polymers such as EPS because it is closely related to the membrane fouling. Uh, the first factor that we have to look at is MLSS, which is a very important biological operating conditions, and in fact, and this is actually the biomass concentration in MBL tank, and this is closely related to the fouling. MLSS concentration is directly proportional to membrane fouling, if other important microbial factors are kept constant. And this is because the cake layer is thicker when the biomass concentration becomes greater. But this hypothesis is only true when under very limited conditions, because if you increase MLSS and other biochemical conditions changes together with this one, so it's just ideal to simply increase MLSS while um, making other conditions constant. So this is why the effect of MLSS on membrane fouling is complicated. So this is just an example to show the effect of MLSS concentration on normalized flux. So this actually shows very ideal result. So if you increase MLSS from 5,000 to 12,000, you can clearly see the decrease in normalized flux, which means we have more foulant. So we have a thicker cake layer formation, so that this fouling occurs rapidly. This is another example. Previously, we just see the result of batch experiments, and in this case, we see that this result of continuous operation. So the PMV profiles are compared, and if you increase MRSS from 3,500 to 12,400, in this case, again the TMF increase faster, which means fouling propensity increases with increasing this amylosis concentration. There are some useful equations that you have to know. In fact, for example, these two guys actually derive some equations to explain the influence of MRSS on MBR performance. Of course, this equation was developed in a side stream MBR, so this cannot be directly applied to the submerged MBR system. Anyway, if you look at this equation, the flux is expressed as a function of Reynolds number and MRSS and MLVSS, and so if you increase MRSS, the flux decrease. The cake resistance can be expressed by this equation. We actually saw the previous equation, which included the specific cake resistance, cake mass per divided by membrane area, and this has the same meaning with this one. So the permeate volume per unit membrane area multiplied by the bulk MRSS concentration. Of course, the assumption is all the MRSS in bulk is delivered to the membrane surface and form the cake layer. So there's no scarring, no back transport, no other effect, and all MRSS are just deposited. The efficiency is 100%. So in fact, this cake mass, cake resistance may be smaller than the result calculated value, because this assumption is very, very limited. As I already mentioned, that this fouling, membrane fouling is not always proportional to the MRSS concentration. And there are many studies to explain this contradictory result. One of the results shows that when mRSS is higher than 10,000 milligram per liter, mRSS concentration correlate well with the membrane filtrability. However, mRSS had almost no effect on filtrability when it is lower than 10,000 milligram per liter. This is probably due to the relationship between mRSS and viscosity, which they propose as follows. So viscosity is given by this equation. So the viscosity of the mixed liquid increased sharply as over 90 megapascal sec when mRSS was higher than 10,000 milligram per liter. Consequently, decreased permeability is due to the high viscosity when mRSS is over 10,000 milligram per liter. However, and the normal condition is the mLSS ranging from 5,000 and 15,000 milligram per liter. And so this means that the viscosity is important, but sometimes viscosity effect may not be important. Flock size is very important. This is one of the key factors affecting this membrane permeability in ambient system. And the flock size can actually changes the permeability of the cake layer. And in fact, if you look at this equation, the head loss in the conventional filtration theory is given. So the head loss is a function of friction factor, shape factor, media porosity, media diameter, filter length, gravity acceleration, superficial velocity. In fact, in membrane systems, we see this kind of equation that specific cake resistance is given by the epsilon given by a function of porosity and particle size and particle density. And this is actually based on this Karman-Cohen equation. And this specific resistance is directly correlated with the cake resistance using this equation, which means the cake resistance is inversely proportional to the scale value, the particle size, scale value for the particle size. So if you decrease the particle size 2 times, the cake resistance increase 4 times. So this is a significant increase in cake resistance. So in other words, the cake resistance is sensitive to the particle size. So the plug size is very important, and if the plugs are broken, in this case the plug size will decrease, so that this membrane permeability will decrease due to an increase in cake resistance. So this is why we have to maintain the microbial plug as steady as possible, and we have to prevent plug breakups, because it will generate the small colloids and cells, and this will actually form a denser cake layer with low permeability. This graph shows the relationship between this cake porosity and cake layer resistance, and as you can see that if the porosity is decreased, the cake resistance increase significantly. So just look at this, the scale for the y-axis, and this is log scale, which means if you simply decrease the porosity from 0.6 to 0.4, we actually have the increase in cake resistance almost 10 times. So you see that this particle size or block size is very important. This picture shows how the porosities of big and small particles are constant. So particle size, the porosity is actually constant if the particle is just spherical. Bigger particles have a small amount of large void space, while the smaller particles have greater numbers of narrow void space. However, the overall void space are equal for both large and small particles. So the cake velocities are equal regardless of the particle size. But if the particle shape changes or the cake layer compaction happens, this porosity may be changed. Here we have a very interesting example showing how we can calculate this cake layer resistance and porosity and other cake properties. So in this case, we just wanted to compute and compare the porosity of cake layers made of different particle size. We have a lot of assumptions which you can just read that, and we also assume that this degree of compression by pressure is same for all samples, otherwise we'll have different porosity for different samples. So first what you have to do is to calculate the cake layer volume, which is from the mass balance, which is given by like that. And for total void volume in the cake layer, we can multiply this one and number of cubes, and then we'll have this kind of this value. So the porosity of the cake layer is given by 0.476. So this is more like an ideal value, assuming that spherical particles and just a very simple this configuration. So the following tables are obtained for different particle block size by a series of calculations similar to these calculations. So if you look at this table, if you increase the block size, the radius of flow, of course, increase. The volume of one block sphere increase. The volume of one block cube also increase. Void volume is increasing, and number of cube in the cake is decreasing, and the total void volume of cake is constant. So the cake porosity is constant regardless of this block size. Here we have different examples to show the relationship between cake resistance and block size using this data. So we'll actually compare the relationship between this cake layer and particle size using blocks which size ranges from 2 micrometer to 500 micrometer, and assuming all ideal conditions and using the equation from this Karman-Kuzeni equation, we can calculate alpha for each cases, and using this alpha value we can compute this cake resistance. And we can repeat this kind of calculation. So we can repeat that. So if we have the product of cake layer and resistance and this one, if we increase the particle size, we can actually have a decrease in this value. So we already concluded previously that this porosity is not affected by particle size. Assuming that this porosity is equal to 0.5, we have the following figures for our C versus particle size, which is this one. So this is cake resistance, this is particle size, and by assuming that this porosity is 0.5, we can actually remove these additional terms here. So what we can confirm is if we increase the particle size, the cake resistance decrease significantly, assuming that this cake mass is constant. So when we have these particles close to 2 micrometers, the cake resistance is almost 5, a very high value. And if we increase the particle size up to 5 micrometers, in fact, this cake resistance decreased by 10,000 times. So this is a huge decrease, which means if you just consider the membrane fouling and membrane permeability, the particles or the plugs with a size of 2 micrometer, with a size of 500 micrometers, this is a huge difference. So again, we have to maintain this microbial plug as large as possible, and we have to prevent the production of submicron particles or the small particles, because they will actually increase the cake resistance, leading to a significant reduction in membrane permeability. Another factor that we have to consider in ambient system is the compressibility of the cake layer, because the cake layers consist of microbial cells and organics, and they are not rigid particles. So they are very flexible, and if we apply pressure, in that case, the deformation of these particles will occur, so that compaction will happen. So these particles are basically compressible, and we have to consider that. So when we don't have any pressure, we'll initially have this alpha value, and if we have pressure, this alpha will increase due to this compression effect. And this compression is difficult to predict by theory, so we just have this empirical equation which has the term P to T to N, which means if we apply pressure, the alpha increase. So by performing the experiments and by having this log-log plot, we can actually obtain this n value, and by using that, we can calculate this cake resistance at different pressures. So this is actually the plot to obtain n value and we change its pressure, and we monitor the specific cake resistance, and the slope is actually the cake compressibility index, which means if the graph is steep, this cake is more compressible, and if the slope is not very large, in this case this cake is not very compressible. Dissolved matters are another foulant that we have to consider in MBR system. Dissolved matters include unmetabolized feed components and metabolite produced during biological reactions. So these metabolites include SMP and EPS. But in terms of fouling, unmetabolized organics or metabolized organics, we cannot distinguish them. So this is why we just deal with these organic matters without any distinguishment for their sources. And dissolved organic matters affect membrane fouling. It's very clear because it can lead to internal and external fouling. And these dissolved organic matters can be adsorbed to the fur surfaces and for walls, which lead to for narrowing. But it can also be adsorbed in the cake layer during their passages through this cake layer. This actually lead to consolidation of cake layer, which make fouling more severe. So this is the figures to show how this cake formation can be altered by these dissolved organic matters. So if we have this cake layer and in fact, if we have dissolved organic matters, these dissolved organic matters can fill the gaps between cake layers, which actually can reduce the porosity of the cake layer. And if you look back to the Carmen-Puzeni equation, if the porosity decrease, the cake permeability decrease, so that this high density cake layer will cause to more severe membrane fouling than the cake layer with loose structures. So this is one of the equations that we can actually predict the flux as a function of dissolved organic carbon. And of course, this equation is an empirical equation, which means we have to determine A and B based on this experimental data. Another empirical equation that some Japanese guys invented or derived is this one. So this resistance in the ambient system can be expressed as a function of MRSS, COD, and viscosity, and these coefficients were determined based on this experimental data. The soluble EVS concentration had been considered a more important factor for fouling rather than DOC. Of course, EVS is kind of a direct foulant, and DOC just include not only EVS but also other foulant which may not be as effective as EVS in terms of this membrane fouling. So this EVS is something that we have to look at. Another thing that we have to consider is the flux structure. In fact, the motivation of using MBL is to operate activate large system when we have the forming or working problems. However, in MBR systems, it's not really easy to overcome these firming, working, and thin flock problems because these flocks not only affect the satiability of the microbial flock, but also it affects the membrane fouling. So the flock structure, the relationship between the flock structure and membrane permeability is very important, and without properly managing these biological conditions and flock structures, the MBL process will fail. So this picture actually shows the microscopic image of these different flocks, and the first one is the normal sludge, which means the particle size is larger, and we can see well-structured, well-formed microbial flocks consisting of many different microbial cells. However, if you experience bulking problems, the microbial flocks disintegrate, which means we can see just a number of small microbial cells instead of the very big microbial flocks. Another problem is, so that's the problem of pinpoint flock, which means the flock is disintegrated. Another problem is the bulking problem, and in this case, we still have microbial flock, but since this microbial flock have many filamentous bacteria, which actually affect the satiability of these flocks. So this is flock, but fully structured flock, so that it's not very good for conventional the activate large operation. As we have already started, the satiability of microbial flock can be measured using SVI, which is sludge volume index. And the way that we can measure is we just compare the volume of sludge in the beginning and after 30 minutes, and we just compare the ratio of the volume, and by doing that we can actually see how easy that this block can be settled. Typical SVI value for pinpoint flock, normal sludge, and bulking sludge range from 50, 100 to 180, and 200, which means SVI, the pinpoint flock. So the access and turbidity of the supernatant after settling could be indirectly related to the flock structure, because pinpoint flock have a very turbid supernatant, while working sludge has a relatively clear supernatant. So in case of pinpoint flock, even if the flocks are completely settled, the quality of the supernatant is the water after settling this solid part, we get this water on top of this sludge, which is supernatant. And in case of the pinpoint flock, this supernatant also still contains a lot of microbial cells, so that we cannot get very clean or clear supernatant in case of this pinpoint flock. So even if this SVI value for pinpoint plug is very small, it does not necessarily mean that this pinpoint plug has very good stability, because the supernatant still contains microbial flux, microbial cells. According to the study of Zhang, this Zhang is actually the Professor Insang Zhang in Hosei University, and he's actually one of my seniors in the laboratory. And when I was in the laboratory in Seoul National University, he was there, and he actually carried out this experiment. And his experiment was actually the comparison of fouling propensity for different microbial flux, which has the conditions of normal sludge, pinpoint sludge, and working sludge. So, interestingly, working sludge has the worst permeability, while normal sludge has the best permeability, and pinpoint sludge is kind of intermediate characteristics between normal sludge and working sludge. And it was found that the dominant factor affecting this cake resistance was our shape, the size of the flux, and the porosity of cake layer. And another guys in other country, they also studied the relationship between zeta potential, SVI, and membrane filterability, and they found that there's no relationship. So it's kind of contradictory result, which can be found in many different studies. But one thing is very clear: the sludge structure or plug structure and fouling propensity, although sometimes we have some contradictory result, but they are very closely related. So without actually understanding or controlling the plug structure, we cannot actually get very high membrane performance in MBR system because of this severe membrane fouling. So we have to consider many different factors such as MRSS, FM ratio, HLT, and of course SVI. Influent characteristics are another factors that we have to consider in designing or operating the MBR system. Typical feed solution should have the ideal ratio for phosphorus, nitrogen, and carbon, and this ideal ratio equals 1:5 to 100. So that's something that these living microorganisms have to needed to have for making their cell body. The obviously unbalanced nutrient concentration negatively affect microbial activity, leading to partial failure in wastewater treatment. Previously, we've studied that this hydrophobicity of the foulant is actually very important, because hydrophobic interaction between foulant and membrane is one of the factors that cause severe membrane fouling. And if the slurry has hydrophobic characteristics, it can actually accelerate membrane fouling. And that's why we have to consider this concept, slurge hydrophobicity. So that, and if you compare different slurges, we see that these slurges have different hydrophobicity. Forming slurge is strongly hydrophobic, And forming sludge is known to have troubles in settling as well as scarm formation in conventional aqueous sludge system in the secondary sedimentation tank, and it also has poor filterability. Although this hydrophobicity of the membranes can be determined by measuring the contact angle of the water droplet on the membrane surface, it is not easy to measure sludge flux hydrophobicity directly because we cannot actually measure the contact angle for the microbial flux. So we needed to have different methods for measuring relative hydrophobicity, and the principle is to use solvent extraction, because if the sludge is hydrophobic, which means we can actually uh, extract this part from water to organic solvent. So by having this solvent extraction, and if you have a lot of stuff that you can get by doing this, which means this sludge is hydrophobic. In the next slide, you'll see the procedures for determining the relative hydrophobicity of a sludge sample. And that's basically the way for this solvent extraction. And organic solvents such as hexane, the octanol, or dimethyl ether is used for this extraction. And so before this solid extraction, after the solid extraction, we actually compared MLSS concentration, and the relative hydrophobicity can be quantified using this equation. So we can just have the ratio between before and after emulsification using this solid using this organic solvent. And again, people have measured this hydrophobicity of active sludge, and normal sludge has a ratio between 54% to 60%, while the forming sludge has the ratio ranging from 62% to 93%. So it's clear that this forming sludge has higher relative hydrophobicity than this normal sludge. So this picture is the way that we can measure relative hydrophobicity for microbial flux. So we put organic solvent here, we put mixed liquor here, just mix it to form emulsion and let it stay for a few hours. Then we can have this clear separation between organic solvent and water, and we can just decanting this aqueous layer, and by collecting this aqueous layer, and we can just measure the MLSS after the extraction, and if this aqueous phase loses a lot of MLSS, which means these microbial flux are highly hydrophobic. As we have already mentioned, many operating conditions directly affect microbial characteristics such as MLSS, EPS, or SMP, and flux structures. And the most dominant parameters determining membrane fouling in MBL are microbial characteristics. However, microbial characteristics are strongly influenced by operating conditions, so that's why we have to look at these operating conditions. One of the typical operating conditions in MBL system is, of course, the SLT. SLT is defined by the reactor volume divided by the influent flow rate, And of course, this is a key parameters determining the reactor performance. And typical ambient system has the HLT ranging from 2 to 5 hours, and which means this biodegradation of organics in the effluent becomes more stable as the HLT increases. And the HLT influence FM leisure. So because we have this kind of relationship, the FM leisure is the leisure between this the total amount of microorganisms in the reactor and this total substrate in the influent, and that can be obtained by having this HLT here. So if we increase the HLT, which means FM leisure actually decrease. So the FM leisure decreases as the HLT increases according to the earlier equation, which results in direct changes in microbial characteristics because the biomass growth rate strongly depends on this FM leisure. And the effluent water quality such as BOD and SS deteriorates, and the settling ability becomes poor as the FM leisure increases. On the other hand, the organic consumption becomes increases as low FM leisures because the microorganisms in the endogenous phase requires huge amount of oxygen for the auto-oxidation of biomass. So the HLT affects membrane fouling indirectly by changing these microbial characteristics. So the way is this, and the HLT affect FM leisure, and by having different FM leisure, we have different stages for the microorganisms. So in endogenous phase, we have rapid biomass growth, and in this declining growth rate, we have very stable growth rate, and in exponential growth phase, we actually have a decrease in biomass, and settling ability becomes poor if we increase FM leisure, and effluent quality becomes also poor with having high FM leisure, and oxygen supply actually becomes moderate if we increase FM leisure. And one thing I have to correct here is, okay, if we have small FM leisure, we have the endogenous phase, which means biomass decrease, and if we have high FM leisures, we have exponential growth rate, which means the biomass actually increase rapidly with the time. Another very important parameter affecting this embryo operation is SLT, and SLT is actually the time that these microorganisms stay in the reactor. So we can actually define the SLT. Here we just say this solute residence time, not the sludge residence time, so it's a little bit confusing. But anyway, we can define this solute residence time, tau E, and if the solution in the reactor does not contain any solute, the solute residence time equals HLT, something like that. If the microorganisms are in the reactor present, such like in a conventional active sludge system, the solute residence time becomes the SLT, which means the mean residence mean cells residence time in the bioreactor. So the SLT is a function of mass of the cells in the bioreactor and the solids wasting rates from this secondary clarification. So if you just look at these bioreactor systems, the SLT is not the solute SLT, salt response time. Instead, we just assume that this is sludge response time, and that's why I'm just telling you that this is confusing. So anyway, here we are talking about this sludge response time or mean cell response time. So in such cases, we can define SLT something like that. And the previous equation is for the conventional activated sludge system. And in MBL systems, in fact, there is no escaping of cells through the membrane. In previous cases, in activated sludge systems, although we have secondary clarification, some of the microbial cells can be just wasted through this secondary clarification because the separation for the cell is not complete using this clarification system. However, in MBL systems, as you know that this is a complete barrier, perfect barrier for microbial cells, so we don't actually have any kind of solid flow in MBL plants. So we can actually change this equation by ignoring this part, so we can just have a very simple equation. So SLT is directly related to the mRSS concentration in a bioreactor. So extended SLT operation lead to an increase in cell residence time, resulting in increased mRSS concentration. This means that the SLT directly influences mRSS concentration, which has already discussed in the previous sections as an important factor affecting membrane fouling. So again, SLT affects mRSS. Of course, it affects other conditions, but one of the way that the SLT affects membrane fouling is SLT affect mRSS and mRSS affect fouling. So this is another indirect factor affecting this membrane fouling. Typical SLT value for conventional activated sludge systems are around 10 days, but for common MBR systems, it's around 30 days. So in MBR system, we have longer SLT, which means MBR system has a larger mRSS concentration, which is close to 10,000 milligram per liter. And it actually reduces FM leisure, which makes these microorganisms in the reactor endogenous. So the membrane fouling becomes less severe under this longer SLT situation. So by changing SLT, we have different stages for the membrane fouling, and generally speaking, if we have increased SLT, the fouling should decrease. But we also have to consider another factor such as EPS. So if we increase SLT, the free EPS decrease because most of the substrate are consumed for the maintenance needs for the microorganisms. This could be one reason why low membrane fouling propensity is observed at high SLT value. However, mRSS concentration increase as the SLT increase, leading to an increase in the viscosity of the mRSS this mixed liquor in the reactor. So we have two competing factors. By increasing SLT, the free EPS will decrease, but viscosity increase and MLSS increase, which will cause, so they have different effects. So that means we needed to have the optimum SLT values rather than just having low SLT or high SLT, because we have this kind of trade-off relationship. Shear stress is another factor that affects membrane fouling, because if we have high shear stress in the reactor, this will disintegrate microbial flux, so we'll have smaller particles and we will have a large amount of free EPS, and then we'll have serious problems of the membrane fouling. And this equation shows how we can calculate shear stress in general systems. So this is actually the ratio between the force and area, and we can actually express this shear stress as a function of this the ratio of shear rate or velocity gradient between two positions. And if you just look at this shear stress near the membrane surface, so the shear stress in Burkitt phase is not good, but if we have very high shear stress near the membrane surface, it will actually prevent the deposition of foulant on the membrane surface. So sometimes we have to calculate, we have to distinguish the shear stress in Burkitt phase and near the membrane surface. And so this is the worst shear stress, which means the shear stress near the membrane surface. And this is the worst shear stress in a feed channel of the recirculation loop instead of the membrane surface. In that case, shear stress can be expressed by this equation, which means if we increase the flow velocity in the system, and we'll have higher shear stress. And this is just an example to calculate this shear stress in a typical side stream MBR system using tubular type membrane modules. And in case of these tubular types membrane modules, we needed to have a very high recirculation flow rates, and this will cause very high, this will actually lead to a very high wall shear stress, and this example shows how we can calculate this shear stress in such kind of system. So this is just the answer. So as I mentioned, that the most dramatic factors of shear stress is plug blockage, because microbial plugs are not very rigid and strong, which means they are more like they are likely to be very fragile. So by having very high shear stress, we'll have we'll have a problem of breakage and disintegration. So this will cause the reduction in flux size and increase in EPS concentration, so that we'll have the membrane fouling. So the effect of this flux size and EPS are explained in this page. So the shear stress by the pump or other mechanical method is not very good for operating this MBR system. So that's why the side stream MBL is not favored by the industry. On the other hand, in submerged MBL, there's no shear stress by the pump. Instead, we have this another we have selective shear stress near the membrane surface, which is created by this aeration. So this aeration is very important in preventing this membrane fouling in these submerged membrane systems, submerged MBL. And these air bubbles have mechanical energy which cause which provide shear force, or we just say this scouring. So it's like that we have this some brushes and we just scrap the membrane surface, and in submerged membrane systems this brush is the bubbles generated by this aeration, and it just scrap or sweep the surface of membranes so that this foulant can be detached. The success of submerged MBL plants depends on how the fouling control strategy is implemented, especially using coarse aeration. Coarse aeration means we have very large the air bubbles, and if we have very small air bubbles, these air bubbles may not have enough mechanical energy to clean up the membrane surface. So we need to have coarse bubbles, so that to generate these coarse bubbles, we have to implement this coarse aeration. But this coarse aeration is sometimes very expensive. The operating cost will increase, and deflocculation would be anticipated. On the other hand, if the coarse aeration is not sufficient, membrane fouling will also become severe. So again, we needed to find the conditions for optimum coarse aeration, because too strong coarse aeration will increase operating cost, and this will also lead to disintegration of flux, because this air also has some mechanical energies that potentially affect this microbial flux. So the strength of this aeration can be measured by this aeration intensity, which is one of these important design parameters for MBR systems. So this is defined as the ratio of supplied airflow rates to the membrane area. And the final factor that we will consider here is flux. Of course, if we have higher flux, we'll have higher fouling propensity. This is based on the idea of critical flux, which was suggested by Field in the mid-1990s. And the basic concept is, if the flux is above a certain value, the fouling rapidly accelerates, and this value is critical flux. If the initial operating flux in an MBL starts as low as possible, the rate of membrane fouling would be retarded. There have been many controversies about what the exact meaning of critical flux is. However, the concept of critical flux in MBLs is simple. The highest initial flux for which TMP remains stable during the operation of the MBL. So there are several methods to determine critical flux, and the common practice is the flux step method, to incrementally increase the flux for a fixed duration as long as each flux steps reach to a stable TMP. So TMP increase indicates greater resistance to permeation provided by a growing cake formation and internal fouling. So the TMP is dependent on fouling parameters described previously, such as MLSS, membrane materials, and system hydrodynamics. Okay, that's all for today's lecture, and we'll talk about the remaining issues in the next time.